Good morning, dear students. Welcome to the virtual class on electrical machine design. And we are basically solving some numericals on the different kinds of machine like induction motor and transformer. And myself, Nalia, I've been teaching at GITS for last 12 years, and let us discuss something new or some more problems on the electrical machine design. I hope you all students are doing well and all are doing well in their good health. Okay, so let us move towards the numerical. So all the numericals which I have been doing here is taken from A.K. Shawnee, textbooks for the electrical machine design, and this is the very good book for your exam preparation. Right. So this was the question which we have been doing earlier. Example number 10.1. This question is related to induction motor, three-phase induction motor. So in the question, they've been asking that determine the main dimension, number of radial ventilating ducts, number of stager slots, and the number of turns per phase of a 3.7 kilowatt 400 volt three-phase 4-pole 5 hertz squirrel gauge induction motor to be started by star delta starter. Work out the winding details. Assume average flux density in the gap is equal to 0.45 Weber per meter square. Ampere conductors per meter is 23,000. Efficiency is 0.85. Power factor is 0.84. Machines are rated at 3.7 kilowatt 4 pole and they are sold at a competitive price, and therefore we have to choose the mean dimension to give a cheap design. Also, we need to assume that the winding factor is equal to 0.955. Stacking factor is 0.9, right? So earlier we had solved this question partially, and it's an induction motor, three-phase, 3.7 kilowatt, 400 volt, 4-pole, 5 hertz. Okay. So let me show you the question solution which we had been solving. Okay. So to solve this, we need to find the mean dimension, and what is the mean dimension? It is the d diameter and the l length of the core. So to find the mean dimension, we apply this formula. Okay, we apply this formula. KVA input Q. KVA input Q is basically given by KW, that is kilowatt, divided by efficiency eta into cos phi. Okay, and now we can just put the values. So we know that the kilowatt rating is given as 3.7 and efficiency of the machine is 0.85 and the power factor is 0.84. So by using these values, we got the value of kVA input Q is equal to 5.18. Okay, then we need to find the output coefficient, which was given by C naught equal to 11 multiplied by kilowatt multiplied by BAV multiplied by AC multiplied by 10 to the power minus 3. So 11 times 0.955, it is the winding factor, multiplied by 23,000 multiplied by 10 to the power minus 3 will give you 108.7. So this is the C naught, that is the output coefficient. And then we have the synchronous speed given by ns equal to twice of frequency by number of poles, that is equal to twice of 50 divided by 4, that is equal to 25 revolution per second. Okay, so till that we had solved, and let us move further. And after that, what we were doing was we need to find the value of D and L. Okay, so we had our NS. Okay, we got our NS, which was equal to 25 revolution per second, and then we also got our output coefficient C naught equal to 108.7. Okay, and then the formula for D square L is equal to Q divided by C naught times NS. Okay, where NS is the speed. So we know the value. We just found our Q, that is a kVA, 5.18, and then divided by, we found our C naught also, which is equal to 108.7 multiplied by 25 revolution per second. So we got our D in square L is equal to 1.91 into 10 to the power minus 3 meter cube. We know that the design ratio is given by the ratio between the L length divided by the pole pitch tau, that is equal to 1.5 to 2. Okay, we can just take the values between 1.5 and 2. So let us take, for a cheap design, we can take this value as 1.5. So L by tau is equal to 1 by 5, and tau is given by pi d by p, where d is the diameter and p is the number of poles. Okay, so we can just put this value here. So we got our L by pi d by p is equal to 1.5, or L by d is equal to 1.5 times pi divided by p, that is equal to 1.5 times pi divided by 4, where 4 is the number of poles. So we got the value of L by d is equal to 1.178. So d square L is given by the value 1.91 into 10 raised to the power minus 3 meter cube. And using these two values, d square L and L by d, these two relation, we can get our value of L and d. So we can just put the value of L. L is equal to 1.178 times d. Okay, so we are just putting this value in this equation. So we got our d cube is equal to 1.91 divided by 1.178 multiplied by 10 to the power minus 3. So we got our d. The value of diameter is equal to 0.177 meter, and the value of length is equal to 0.13 meter. Okay. So till that we had done this numerical, and now we shall be doing further. Okay. So let me move to the new page of my whiteboard. Okay. So we know that the pole pitch given by tau is equal to pi times d divided by p, that is number of poles, that is equal to pi multiplied by 0.12, which is the value of d diameter, and divided by the number of poles, 4. So we got our pole pitch, the value of that is equal to 0.094 meter, right? And we know that the length of the core, the length of core is 0.13 meter, and then we can provide, and therefore we can use one radial duct for the ventilation purpose, one radial duct, 10 millimeter wide. Okay, which is provided. So the net iron area, the net iron length Li is given as 0.9 multiplied by 0.13 minus 0.01, that is equal to 0.108 meter. Okay. The next which we have to need to find is the uh, turns per phase. So we need to find the turns per phase. Okay. So we know that the flux per pole, flux per pole, phi m is given by this formula BAV, which is the magnetic loading, multiplied by length, multiplied by the tau, which is the pole pitch. And this value will be equal to 0.45 multiplied by 0.13, and this will be multiplied by 0.094. That will be equal to 5.5 into 10 multiplied by 10 to the power minus 3 Weber. Okay. Now we know that the machine is started by star delta starter. Started by star delta starter. So we have to design for delta connection. Okay, so we know that the stator voltage per phase given by ES is equal to 400 volt, right? So you can just note down this. Okay, so you have taken the notes. So let us move forward. Let me take a new page. Okay. So we know that stator turns per phase stator turns per phase TS is basically given by the formula ES divided by 4.44 into the multiplied by frequency multiplied by the maximum flux density or maximum flux multiplied by the winding factor kWs. Okay, and this we can just put the values here and we can get the TS. The value of TS will be equal to 400 divided by 4.44 multiplied by the frequency, which is 50, multiplied by the flux 5.5 into 10 to the power minus 3 multiplied by 10 to the power minus 3 multiplied by the winding factor 0.955. Okay, so solving this, you can get the value around about 343. Okay, so just write it down. Okay, so you have written that, and then next let us move towards the number of stator slots. Okay, the number of stator slots. Okay, so we need to find this out. So how can we do that? We can just assume that it's a small size machine. It's a small sized machine, and we can use here semi enclosed slots. We can use here semi enclosed slots, and therefore the pole pitch, or you can say the slot pitch, can be less than 15 millimeter. Okay, but it should not be less than 10 mm. So the slot pitch should lie between 10 millimeter and 15 millimeter. Okay, so let us take slots per pole per phase, which is given by QS is equal to 3. Because we have 3 phase, so we can take slots per pole per phase equal QS equal to 3, and total number of stator slots, which can be given by SS, is equal to 3 into 4 into 3, that is equal to 36. Okay, And then we can also write that stator slot pitch given by YSS is equal to pi times diameter divided by SS. There is a number of stator slots. That will be equal to pi times 0.12 is the diameter divided by 36. And that shall be equal to 10.47 millimeters. So that is a good value, and it is well under the defined limits of 10 mm and 15 mm. So our stator slot pitch is lying between 10 mm and 15 mm, that is 10.47 millimeter. And that we wanted. Okay. So you can just write down these things. Okay, so we have just calculated the number of stator slots, and we also got our stator slot pitch, which is 10.47 millimeter, right? So now we need to find the total number of stator conductors. That we take a new page. Okay, so the total number of the total number of stator conductor, total number of stator conductors, that will be equal to 6 times TS. That is 6 times TS is 343, the stator slots. Yeah, 343. TS is the stator turns per phase. Okay, so this is the stator turns per phase. Stator turns per phase. So that is 343. So 6 times 343. That will be give you a value of 20 or 2058. That is the total number of stator conductors. Okay, then we need to find the conductors per slot. So that is equal to the total number of slots. Conductors per slot is given by ZSS, which is equal to the total number of stator conductors are given by 2058, which can be divided by the total number of slots, that is 36. So this will be equal to 57. So 57 is the conductors per slot. So actual number of turns per phase, actual number of turns per phase, TS can be given as 36 times 57 divided by 2 times 3, which will be equal to 342. Okay. And the last thing which we need to find here is our winding details. So our winding details can be we can find it out. Okay. So for small machines like this, for small machines, we can use a single layer mush winding. A single layer mush winding placed in semi-enclosed slots. Semi-enclosed. Okay. And each coil here will occupy 2 slots. Okay. And therefore, number of coils for 36 slots will be equal to 36 divided by 2, that is equal to 18. Okay, right. And number of coils per phase, number of coils per phase, number of coils per phase can be given as 18 divided by 3, which shall be equal to 6. So we can see from this given data that as there are 3 slots per pole phase, or we can say 9 slots per pole. Nine slots per pole. The coil span is 9 slots. The coil span is 9 slots. Coil side in slot 1 is connected to coil side one plus 9, that is equal to 10. In slot 10. And actually the coil span in mush winding should always be an odd number, should always be an odd number in terms of slot span. In terms of slots spent. So Therefore, it will be odd. Here it is odd and is equal to slots per pole, and therefore the coils are full pitch, and therefore the coils are full pitched. Okay, so I will just show you the actual diagram of the winding diagram. Okay, just give me a minute. Okay, so dear students, you can just see the winding diagram. The winding which we have designed will be just I'm showing you. This will be the type of winding, and these are the slots. Slots number 1, 2, 3, 4, 5, 236, and then we have the windings here starting from SR. Then we have FB, SY, SB, FR. Okay, these are the number of slots are given, and the winding type of. This is the mesh winding. Okay, it's a diagram of the mesh winding. It is also single layer, and here each coil is occupying only 2 slots, and they are placed in the semi-enclosed slots. Okay, so this is the winding which we have been using. Okay, right. So that was about this numerical, and then let us move to the next numerical. Okay. So find the main dimension of a 15 kilowatt 3-phase 400 volt. Okay, find the main dimension of a 15 kilowatt 3-phase 400 volt 50 hertz 2810 rpm squirrel cage induction motor having an efficiency of 0.88 and a full load power factor of 0.9. We have to assume the specific magnetic loading, which is given as 0.5 Weber per meter square. The specific electric loading will be given as 25,000 amperes per meter. And we can take the rotor peripheral speed as approximately 20 meter per second at synchronous speed. Okay, right. So we just need to find the main dimension of a 15 kilowatt 3-phase 400 volt 50 hertz machine with it's a squirrel cage induction motor, and it has a speed of 2810 rpm. The efficiency is 0.88 and the full load power factor is 0.9. The specific magnetic loading can be assumed as 0.5 Weber per meter square. The specific electric loading can be assumed as 25,000 ampere per meter. And we can also take the rotor peripheral speed as approximately 20 meter per second at synchronous speed. Okay, so let me do this numerical. Let me take a new page. Okay, so we know that it's an squirrel cage induction machine, induction motor, 15 kilowatt, 3-phase, 400 volt, 50 hertz. So we know that the KVA input is given as Q equal to 15 divided by 0.88, which is the efficiency, multiplied by 0.9, which is the full load power factor. So that will be around about 18.94 kVA. Okay. And then we will have the output coefficient. The output coefficient can be given by C naught, which is equal to 11 times the winding factor Kw multiplied by the specific magnetic loading multiplied by the specific electric loading AC multiplied by 10 to the power minus 3. So this we can find out C naught will be equal to 11 times. The finding factor is actually given as 0.955 multiplied by 0.5, the BAV factor, and the AC factor is 25,000, which can be multiplied by 10 to the power minus 3. So we will get our C naught, the output coefficient, is equal to 131.3, Okay. So here then our speed, the speed the speed of the rotor, the speed of the rotor at full load is given as 2810 rpm, and the nearest synchronous speed nearest synchronous speed which corresponding to 50 hertz is 3000 rpm, right? So we can actually find the synchronous speed. We can just find the synchronous speed ns, that will be equal to 3000 divided by 60, which will be equal to 50 revolution per second. Okay, so we got our ns also. Let me take a new page, and then we can just find the value of d square L. We know that the product d square L is given by this formula, Q kVA divided by C naught times ns. So we know that d square L will be equal to Q is we got our Q is equal to 18.94, which can be divided by our coefficient, output coefficient C naught. We just found out it was 131.3 multiplied by our ns, which is 50. So this will be our d square L will be equal to 2.88 into 2.88 multiplied by 10 to the power minus 3 meter cube. Okay. And now this is the important point. The rotor diameter. The rotor diameter in an induction motor. An induction motor is always equal to the stator bore. Is always equal to the stator bore. So we know that our pi times diameter multiplied by the speed ns is equal to 20, and from that we can just find our t equal to 20 divided by pi times 50, which will be equal to 0.1257 meter, and hence our length L will be equal to 2.88 into multiplied by 10 power minus 3 divided by 0.1275 to the power 2 which will be actually equal to 0.177 meter. Okay, so we got this question also, and I hope you understood this question, and I think you can solve it also yourself also. Okay, so that's it. Just let me revise you how we solved. What was our question? The question was to find the main dimension of a 15 kilowatt 3-phase 400 volt 50 hertz 2810 rpm a squirrel cage induction motor having an efficiency of 0.88 and a full load power factor of 0.9. We are assuming these things. The specific magnetic loading is given by 0.5 Weber per meter square. The specific electric loading is given by 25,000 ampere per meter. And we can take the rotor peripheral speed as approximately 20 meter per second at synchronous speed. Okay. And then we got our KVA. The KVA input Q can be given as 15 divided by 0.88 times 0.9, that was equal to 18.94. Right. And then we got our output coefficient, which was equal to C naught given by 11 times the winding factor multiplied by the BAV multiplied by the specific electric loading times 10 to the power minus 3. So C naught was equal to 11 times 0.955 times 0.5 times 25,000 times 10 to the power minus 3, that is equal to 1.3, and the speed of the rotor at full load is 2,810 rpm, and the nearest synchronous speed corresponding to 50 hertz is 3,000 rpm. So we got our synchronous speed n is equal to 3,000 by 60, that is equal to 50 revolution per second, right? And then we got our product, that is d square L, which is actually given by Q divided by C naught, that's output coefficient, times ns speed. So we got d square L is equal to 18.94 divided by 131.3 times 50, that is equal to 2.88 into 10 to the power minus 3 meter cube. And the rotor diameter of an induction motor in an induction motor is equal to stator bore. So we got our pi times d times ns is equal to 20. So we got our d is equal to 20 divided by pi times 50. So that is equal to 0.1257 meter. That's our diameter, and the length is equal to 2.88 into 10 to the power minus 3. 2.88 multiplied by 10 to the power minus 3 divided by 0.1275 to the power 2, that is equal to 0.177 meter. Okay, so we got our diameter and the length for this given induction motor. Okay, right. So we shall be discussing more questions in the next class, and I hope you enjoyed the class this semester. You should be very careful, and you can solve more questions in your books. Okay, right. So thank you so much for attending this class. Okay, goodbye to all of you. I hope you're doing well. Okay, bye bye. Take care. Okay, so this was our virtual class on the electrical machine design, and we shall meet soon again. So bye, goodbye, take care.